So now, well, you see at least SP logic here on top of the first slide. So these are the things I claimed yesterday, but with a bit more nuance. So, for example, the last claim was that all knowledge ultimately results from defeasible reasoning, which is not the same as the fact that it goes backward or is justified by defeasible reasoning. Okay, so we have talked enough about that yesterday. So, logicians have almost only worked about deductive logics. If you look at any logic journal, you will see that most papers are about deductive logics. So basically tasky logics that are reflexive, transitive, and monotonic. There is some literature on defeasible logics, but these are rather fragmentary and a bit disparate. For example, books on non-monotonic logics have been published, especially by computer scientists. And a typical book in the old days, 20, 30 years ago, was, I now remember the man's first name, Witold Łukasiewicz. You look like amazed or no, you, yes.
Yes, I think much about that. What?
You don't like the book or you think it's not representative or?
I think more closely about that.
So if you look in the book, then you will find that there are some very direct approaches that are almost describing computer programs. And then there are some more theoretical approaches that come a little bit closer to logic, but it's hardly logic. It does not have what we are used to. It definitely almost has never meta theory in it. Also, the syntax is often either absent or not well pronounced. Sometimes the same holds even for the semantics. But anyway, so I always found this as a kind of missing point that should be repaired. Now, a few peculiarities about defeasible reasoning, I've hinted to them yesterday. The first thing is that there is always, in defeasible reasoning, there's always an internal dynamics. So conclusions are drawn at some point in the reasoning and may be revoked later. And typically they are revoked because by deriving more things from what we had, from the premises, by deriving more conclusions from them, we see that a conclusion we drew at, say, line 5 of the reasoning was not correct. But we see it only with hindsight. And you can show that if you have really a defeasible reasoning form, that then you cannot phrase it differently. You cannot catch it, for example, in terms of a tasky logic. It needs to have this internal dynamics, and this internal dynamics is always rather fundamental, and more fundamental than the so-called external dynamics, which is simply non-monotonicity. So that means if you have a premise set and you draw conclusions from them, and then you add some premises, you get new information, then it's possible that some conclusions you drew before do not follow anymore. So, in other words, if it is monotonic, then every extension of the premises gives you at least all the consequences that the premises have. If it is non-monotonic, then some consequences may be taken away. And the fact that logic is non-monotonic that it has this external dynamics shows that, in a sense, provokes the internal dynamics. Suppose that these ideas were already in from the very beginning. So maybe I will have to now and then use the blackboard, sorry. So suppose you had a premise set gamma, and then here are some new premises A1 to AN. And the thing is, normal tonic means if you add these to gamma, then you get entropy. You may have to revoke conclusions you derived in an earlier point. But now suppose you start with gamma union A1 to AN. You start from the very beginning, like that. Well, not in this form, but you start with, let me phrase it like this. You start with the premise set delta, from which by some Tarski logic, I will specify in a few minutes which one. So some Tarski logic gives you these things from delta. Then it's possible that you do not see that only after you are reasoning for a while, you figure out that actually A1 to AN are consequences of that. You may not see it just from the very first beginning. And then at that moment, this mechanism will start playing. You will say, then we have to withdraw some conclusion. So if it is non-monotonic, then it is understandable that you have this internal dynamics. And actually the internal dynamics is fundamental and general. And then another point that is mentioned there concerns the weak consequence relation of Russia. So the idea is if you have an inconsistent set, so suppose that you have a nice wiper here somewhere. Is it over there? Yeah. So suppose now that gamma is an inconsistent, is a premise set, and you find out that it is inconsistent. Then the idea of Russia goes, and you find it also in other people in the 50s and 60s, to split gamma up in maximal consistent subsets. So you take consistent subsets, that's quite simple, and then you add members of gamma to it until it explodes, until it becomes inconsistent. These are the maximal consistent subsets. Then you can define that from gamma follows by the strong consequence. That's how Russia does it. Follows A if and only if for all maximal consistent subsets, this is a notational abuse, of course, for all maximal consistent subsets of gamma, you can derive A from them by classical logic. And then you can also do this, the weak consequence. Then you have here, there is a maximal consistent subset of gamma from which A is classically derivable. So, of course, since classical logic is monotonic, and that masters what follows from a maximal consistent subset, if you extend your gamma, whatever follows from gamma will still follow, because there is always a maximal consistent subset either of gamma or of the extension of gamma. So if after gamma has been extended, the maximal consistent subsets of gamma are still subsets of the extension, first of all, and next are still consistent. So whatever follows from one of them keeps following after the extension. So this weak consequence of pressure is monotonic. Nevertheless, you can show that it displays an internal dynamics. So you cannot characterize it by Tarski logic, but only by an adaptive logic. Oops, sorry. That was a bit too fast. I better use the. The basic idea behind the internal dynamics is that your insight in the premises grows. And this sounds like a metaphor, but it is not. I have a paper published in Logic Analysis somewhere in the 90s, I think, or even in the 80s, where the idea of the information provided by a proof at a certain stage. So you have written down some premises and the applied rules to draw consequences from the premises or from previous lines. Then you can show that as this goes on, your knowledge increases. Your insight in the premises increases. You can show it in terms of that paper. Which is kind of interesting because in the old days, you remember the definition, a deductive consequence is a consequence that follows because the conclusions you can draw, the meaning of the conclusions is included in the meaning of the premises, they often say. So that means deduction leads to nothing new. Kant already noted this and thought that this showed that logic was actually a kind of anti-enterprise, uninteresting enterprise. The person that reacted to Kant in this respect, you may not expect this, but the person that reacted to Kant was actually Schopenhauer. He defended logic. He said, Kant is thinking that logic is so simple that everybody sees whether something is a consequence or not. But people have made mistakes and mistakes over the centuries and go on until they grow very old and wise. Okay? So that Kant said more funny things, apart from the fact that he also had some very important and good epistemological insights. Good.
Kant also said that the world was obviously Euclidean.
Yeah.
So,
well, that we as human beings would be unable to think the world or to observe the world except from a Euclidean framework. That's one of his stupid claims, yes.
Mistaken. May I ask the title of the paper you mentioned, the one you wrote in the 80s or 70s?
Rasher?
No, you meant a paper on the information provided
yes.
by the arrival. I remember it appeared in Logic Analysis, maybe I can quickly skip to the very end, and otherwise I can find it on this computer using the internet. So I will definitely give you an answer. But I do not even know by heart when it. No, that's not it. That's a Lukasiewicz book. No, I didn't. But when we come to the question time, and then I will, because my bibliography is of course on the internet, and I will check there and I will soon find it. Yeah, please, go ahead.
It's the discussion just about
Sorry, I'm afraid.
Being distincted in his complaint about our confusion about is this relevant to the activities and like something?
It's not relevant to adaptive logic. It came up in a discussion because, well, we were saying that Kant said very important things, but also a few not so important and actually mistaken things. Okay, we go back to the introduction. Oops, that was not the idea. Now we are in the LaTeX file. These are basically told yesterday, so I will present what came out of it in the end was a unified framework for that is I now call adaptive logic in standard format. In a sense, adaptive logics are especially useful to formalize or formally capture methods and handling inconsistency in the way it will happen here was not known beforehand as a method. Okay, so in that sense, it was an atypical example. The first adaptive logic was an atypical example.
Would you like to know?
Sorry?
Would you like to help you try the slide? Too much.
You think it is? No, I can just as well use this. I think it is. It will not make much of a difference. I'm sorry. Thank you very much for trying. So, during the development of these adaptive logics, the Ghent group has tried to integrate many known methods, like for example, with respect to handling inconsistency, these rational manner methods have been characterized. Again, if you ask for the, I usually call them rational manner logics because Ruth Manner was an old friend and she had done a lot of work together with Nick Rusher and published several papers, for example, in Theory and Decision. The first volume, you have a paper by the two of them. And I like to add her name because, well, there are always, well, very often in academia, there are certain misunderstandings. And let's say that Nico was is a very famous philosopher, did not always treat her as he should have done in my eyes. Okay, this is to some extent a subjective claim, but I kind of wanted to support her. In the end, she ended up working on the logic of questions, but I think she deserved more credit than Nick gave to her. I've known Rasher also for a very long time, so this has nothing to do with animosity. I met him personally in '72 and even went to Pittsburgh for a year to study with him on philosophical logic. Okay, so we have integrated certain existing approaches to methods, and then we have also developed a lot of new things, or sometimes in collaboration with other people. Like there are a lot of adaptive logics on deontic paradoxes, for example. Like you can have a law in a certain country and you can adhere to a certain religion that gives you, and this may conflict. So the law can force you, for example, to become a soldier, and if there is a war, to go and fight, and your religion can forbid you to kill other people. Except in some extreme cases that are not provided when there is a war. And so there are means to resolve this. Of course, you have to assign certain preferences. Yeah, I'm terrible at this. Now, as you all know, classical logic and most predicative deductive logics are semi-recursive consequence sets, but not recursive consequence sets. So that means there is a positive test. That's the terminology used by the original Boolers and Jeffrey books. When Burgers came in, he scratched out positive test everywhere and replaced it by semi-recursive. So the idea of a positive test is that you can put a Turing machine working, and if there is a proof of ifs, for example, something is a theorem of a certain logic, then your Turing machine will find that. If it is not a theorem, the Turing machine might say it's not a theorem or might not go on running forever. And of course, I think it's good. I hope that let me mention very quickly the idea. If you remember Gödel's proof, every proof has the proof of Gödel's incomplete distilled. Every proof, formally, syntactic formal proof of a logic has always a Gödel number. So you can very easily devise such a positive test. You start by 0, and then if that doesn't work, you go to 1 and to 3 and so on. And you decipher the thing as a Gödel number, and you see whether it is the Gödel number of a proof. And if it is, then you see whether the proof is correct in classical logic, for example, in Gödel's case. And if it is, then you say the last or the formulas that occur in the proof are theorems. Okay, that's a very simple way to show rather trivially there is a positive test. Just go through the natural number. Now, very typically for defeasible logics, there is no positive test. In other words, they are not semi-recursive, but I think the positive test is more appealing here. And this is what causes the internal dynamics. Namely, that at some point in the reasoning, you cannot decide whether some formula is derivable or not derivable, given your rules of inference. There's no way to decide that. Okay. Sometimes there is a negative test, sometimes there is not. It's also possible that a formula is derivable in several ways. That's also a possible complication. So for some defeasible logics, neither the consequences, the L consequences of gamma, nor the complement of it, complement with respect to the set of all formulas, both may be semi-recursive. And then this is about complexity that I mentioned already yesterday. It was proved that for some adaptive logics, the consequence set of some premise sets is pi11 complex. So it means you can characterize very complex theories by this means. Now, if you try to devise a syntactic approach to adaptive logics, there is a danger to run into circularity. Because, well, it was already mentioned on a previous, what you often will try to get in your rules is something like, from these formulas you can derive another formula, unless if a third formula is derivable. But of course, that's obviously easily seen to be circular. Okay? So the solution to that is to make a distinction between two notions of derivability. On the one hand, you use a kind of basic logic that in adaptive logics we call the lower limit logic, and you say the adaptive rule is from a set of premises, gamma, or from a set of formulas, gamma, you can derive a conclusion A, unless by this, so that's the rule of the adaptive logic that says so, you can derive B, unless if, you can derive A equals, unless some formula B is derivable by the lower limit logic. And this lower limit logic is simply a Tarski logic, so that is often not too complicated, well, less complicated to check out whether that is the case or not. Then, as I announced, the thing was generalized, and then the idea was people had already intuitively the idea what you do there to explain handling inconsistency can also be applied by characterizing things like abduction. So I phrase it now at once in the standard format that actually originated only like 20 years later. So the idea is that you characterize an adaptive logic as a triple. On the one hand, there is a lower limit logic, LLL. So that's a logic, a Tarski logic that is defined over some language. L is reflexive, transitive, monotonic. It is also, apart from being Tarski, it is formal and compact. But only the notion of formality can give some problems here, because sometimes people claim a formal logic is a logic in which uniform substitution holds. No, that doesn't work too well. That's not a very good claim or not a very good definition. Why? Because, well, you cannot use uniform substitution to characterize predicate logic. Uniform substitution works at the level of propositional logic. There are two poles from Krakow that actually well, two Polish people, maybe I should say, that in one of the journals of Krakow University, namely, I'm not sure, I don't remember, I'm sorry. But in one of those journals, they tried to approach predicate logic in terms of uniform substitution like roots. And what they came up with was extremely complicated, with lots of exceptions and so on and so on. So I've propagated that paper in many papers of mine, and I would say check first, look for that paper, and check whether you want to have that or not, because it is quite complicated. But of course, that a logic is formal simply means that there is a formal criterion to decide whether something is valid or not valid as an inference in that logic, or is a term of the logic or not. There is a formal criterion for it, and for example, it could be if you write down a set of premises and a conclusion. When you write down something like this, you can easily define functions that map every set of letters in your logic on themselves. So propositional variables, you take a function from propositional variables to propositional variables. You do that also for predicate letters and for individual constants and so on and so on. And then you say, if I systematically replace in the whole expression, so systematically means you do it everywhere. If I systematically replace every letter by what this function assigns to the letter. then if this is valid, the result should still be valid. That's a formal criterion. It does not warrant, by no means warrants uniform substitution, but it is a strictly formal criterion. So if a logic has that property, then it is clearly a formal logic in a very sensible sense. I pressed this a little bit because there was, in the old days, a South American person whose name I forgot, so I cannot even name him. But he told that the fact that you could not apply uniform, for example, in adaptive logic, if you have P and Q, you cannot derive from this. No, I need a bit more, sorry. P and Q and maybe Q or R. Not Q or R. You cannot derive from this. Maybe I'm telling this a few minutes too early. You cannot derive from this R because according to paraconsistent logics, disjunctive syllogism is not always correct, according to nearly all paraconsistent logics. So, of course, if you, what you actually have, and now I jump a little bit since I'm sorry. What you actually have is that if Q and not Q need not hold on the premises, then it is possible that not Q and Q are both true. And in that case, R can be false and all your, well, if P, Q and not Q are true, then R can easily be false. And so these can all be true while R is false. So at least from a semantic point of view, it should not be a consequence. Now, if you would be allowed to apply uniform substitution, you could replace P by not Q. And now you have a problem, of course, because from these you can derive P, Q and not Q. So, which you could not before and was essential for holding the let me try again, and maybe I should write on another blackboard because people over there are kind of staring. Suppose you have P, Q, and not Q for R. So according to classical logic, you can derive R from this, because and according to an adaptive approach, you can also derive R. You just say, well, there's no reason why P and not P should be both true. Okay? Sorry, there's no reason why P and not P should be false. It is very well possible that P is true, Q is true, and not Q is true, and then R can be false, as I said before. So that means from this you can derive P or Q and not Q. So either R will have to be true or Q and not Q will have to be. And the idea in adaptive logic is then that you push this part to the side as a condition, and that you say this is an abnormality, a contradiction, and that you say from these three I can derive R on the condition that Q and not Q is false. Can Q and not Q be false on these premises? Yes, very, very much. Okay. But suppose now that you replace P by not P by uniform substitution, as those people wanted to do, then the result is that now Q and not Q cannot anymore be avoided. It has to be true because it follows directly from, sorry, not Q. It follows by conjunction from these two. So this cannot be held to be false on those premises. and as a result of that, you cannot derive R anymore. Okay? You cannot be certain that R is true. Even if you suppose as many contradictions as possible to be false, still R can, okay? So some people thought this shows that adaptive logics are not uniform or are not formal. But they are formal because you have this slightly more complicated criterion, which I think is more basic that I gave a minute ago. So it always helps to go to a conference and people telling you these things are no good because they are not formal logics. And then you start thinking and you have to solve the problem. So please be critical. Tell me I'm wrong. It is useful also to add something we call the upper limit logic. If you suppose that all abnormalities are false, in this case, that contradictions are false, and you add that to the logic, for example, one way to add it is by saying A and not A. From there you can derive anything. So then you are sure that, well, Grand Priest will like to push what this means is really that A and not A cause triviality. If A and not A are true, then triviality is bound to be true. Which, yeah, well, this is an, you can say yes or no, it depends on your idea of what is a model and things like that. Do classical models, is there, well, we know that if to classical logic you add the trivial model, the model in which every formula is true, you still have the same logic, semantically speaking. At least if you, yeah. But what this thing says is you can also put it in the context of adaptive logics that are, well, lower limit logics, paraconsistent logics that are defined as fragments of classical logic. Then you can also write it like this, of course. It's a theorem that A and not A implies B. Because in that case, you simply keep the deduction theorem completely and unchangeably. If you give material implication its full and original meaning, then the deduction theorem keeps holding. So if you add this theorem to most paraconsistent logics, you just get back classical logic, which is the upper limit logic of most inconsistency adaptive logic. Okay? I think that everybody knows what a paraconsistent logic is, and I hope everybody has once seen at least the whole idea. If you have A or B and not A, then according to classical logic, you can derive B because A and not A cannot be true together. If they can be true together, of course, well, take a model in which they are both true, A true and not A true, then B can easily be false. So B does not follow anymore in that case. What the adaptive logic actually does is it says, let's try to minimize inconsistency, interpret the premises as consistent as possible. And then if you do that, then you will make either A or not A false, and then B will have to be true, because otherwise the first premise becomes false. Now, what is the use of this, or what is the idea behind it? Think about a point where, in the development of some discipline, you reach an inconsistent theory. Well, as I pointed, as I referred to yesterday, people like Grant Priest will say, fantastic, now we have an inconsistent theory. And that's no problem because we have paraconsistent logics. Well, I think that you can show that if you can get rid of the contradiction, you get a better theory. If you can get rid of the contradiction without losing any information that is contained in your theory. So I think that actually, and I also think you can show it from the history of the sciences, if people find a contradiction in their theory, they will try to get rid of it. Okay, so Frege thought he had a disaster when he got his letter from Russell pointing out that he had a contradiction in his theory and started adding things to an appendix before it went to the publisher actually. And I think you can justify this, that there are good reasons to do so. But then the problem is, suppose you think that the mainstream view is correct, that you should try to get rid of your, which I believe actually, that you should try to get rid of inconsistencies. Then how should you proceed? Well, a first step would be, you will proceed in 2 steps. The first step will be to identify the inconsistencies and to localize them, to say, there is the inconsistency. It comes from those premises. It derives from, not from just a set of premises, but from premise 1 and premise 7, for example. They give you the contradiction. And that's the first step, minimize the inconsistency, so meaning localize them. And then the next step is try to get rid of the inconsistency. Okay? So change something to your premises in such a way that you can easily think about this in terms of, well, you can easily think about this, what I refer to in Frege's set theory. You can discuss whether it's a set theory or not. For example, Ottavio Bueno refuses to call this thing a set theory because he says that was not Frege's intention. Yeah, well, that's maybe correct, but it has 2 actions. Extensionality and abstraction. So, looks like set theoretic axioms, right? They are even in CF. So, excuse me, yes?
Yeah, actually, main meeting, Sandra, my colleague, she was telling me during lunch how to identify this inconsistency, right? Like, if it is, because you know that recognizing that a set in classical propositional logic is inconsistent is not practical. Computational complexity. Some principles easy at all in an objective sense to identify. Right? So,
I'm now just talking about applications. So, at several historical points in time, we have seen that certain theories are inconsistent because we derived an inconsistency from them. The fact that you cannot beforehand guarantee that if I give you a theory, you cannot show that the theory is consistent. That's correct. There's no positive test for consistency. That's why you need an adaptive logic for the thing and not a tasky logic. But that does not mean that at certain historical points, for example, it's clear that Russell showed Frege's set theory, if I continue to call it like that, showed it inconsistent. In the middle of the 19th century, thermodynamics was inconsistent. And this inconsistency was revealed by Clausius, German thermodynamicist. If that is English. And actually, when you look at Clausius' paper, one of my former students, that actually is now my successor in Ghent, wrote a paper on that in Logica Analyse. I should again check on the internet when exactly the paper appeared. But she made a study of Clausius's work after being in Thessaloniki, where there were Yorgos Boudaroulis and also people in Athens had worked on thermodynamics and were especially interested in thermodynamics for a reason I never understood very well. But okay, because thermodynamics is now complicated in the 19th century. Of course, like many people, even some handbooks even ascribe the so-called second law. Please, yes.
Yes, I would like to ask you, you said you should avoid contradictions if you can, which is fair enough, I think. And then we should localize them. But sometimes contradictions are not as clearly internal to the system, right? You can have a contradiction from one of your backgrounds or positions and your system. And in those cases, I don't think there will be a formal approach that you can get because your background assumptions are usually outside your system. So is there a way you can introduce that in adaptive logic?
I see no principled objection, why not? Yeah, it's a sensible question, but I do not see why, well, you can, it's possible that one half of your inconsistency comes from something that does not play an essential role in the theory itself. That's quite possible. But let me just finish this sentence on what the open makers did in Clausius. So she having been in Saloniki, where there were also students of Yorgos that had worked on thermodynamics, she had some insights in it and started following the reasoning of Clausius. Clausius's paper is about 90 pages, so it's really a kind of monograph. And there he, in a sense, saves the theory of Carnot by introducing, for the first time, by adding something he calls obvious. And he says, I want to add it to my theory. And the obvious he adds is that heat does not by itself go from a cold source to heat to a hot source. So heat can fall, as it were, from a hot source to a cold source, but not vice versa. And indeed, that's the second law. So if you add that to Carnot's theory, then he was able to solve the contradiction he got. But the interesting thing is that he starts a reductio. So he has the theory of Carnot plus a number of things by Gibbs, and these were known to conflict with each other. For example, in Carnot, you had the preservation of heat, whereas in Gibbs, you have more sensible things. So he starts by introducing a hypothesis and then derives a contradiction, B and not B. And then instead of concluding A is false, he concludes, of course, this is nonsense. And then replaces A by C. Finds again a contradiction, D and not D. And then derives from this not C. And says, UP, we are there, problem solved. Now, what was the first problem? The first problem was that B and not B, that stood here originally, were derivable from the theories, from what he took from Carnot and from Gibbs, were derivable from those. So the hypothesis has nothing to do with it. In that case, there's no reason to reject the hypothesis because it doesn't play any role in it. And this you can very easily understand from the point of view of adaptive logic. So if you apply the adaptive logics to nearly any paraconsistent logic, you will come to the same conclusion. So, of course, I do not claim that Clausius understood adaptive logic. For him, it was a kind of intuitive fluke, okay? But it is kind of nice and funny to see afterwards that you can, this puzzling thing of this is nonsense and now we can apply reductio, you can understand that from the point of view of inconsistency adaptive logic. Okay. Sorry. For people that think that this is porn, it is actually porn, but it is also the most famous painting in the Antwerp Museum. It's the Madonna by Fouquet, so it's also a religious painting. And we know the woman that stood for that posed for the Madonna. Her name is Agnès Sorel, and she was born in 1422. There's also a painting where there's just Agnès Sorel in the same position, but without little Jesus on it. That was the real porn in the 15th century. Okay. Well, at least before there was something more ugly on my computer. So, Maria Martina Zordas, that some of you know, she was able to replace the awful thing on my computer that Microsoft had put there by this painting. I'm not able to do that. It's too complicated. Okay, yes?
Yeah, Professor. Those stories make me think, remind me of a short story I once read, which is actually a long-standing trope in mathematics, but anyway, it's a short story about this woman, a mathematician, which falls into a deep depression, her marriage ends, and well, everything is terrible, and all throughout the story, she's showing some calculation she's done to her colleagues, and none of them can find an error. And in the end, it is revealed that, well, that calculation showed in arithmetic that 1 equals 0, so that the whole mathematics is inconsistency or whatever. And I always think about that if we indeed found that, I don't know, CF is inconsistent, I think that absolutely nothing would happen. It's an absurd belief, but anyway, why do I believe it? Because we have managed to use it until now, right? If there is an inconsistency, it is so complicated that it barely affects the everyday practice. So, I don't know, I think about the defeasible reasoning, and you said something that comment by someone about complexity. If inconsistencies are so complex to find, perhaps they are not so relevant to another part of the logic. And you care to comment?
Yeah, still I think if even inconsistency would crop up, everybody would consider that as a problem. On the other hand, I think you are right, and I even have a paper in which I try to show that you are right, even before I knew you. Namely, it's a paper appeared in a fellowship for Jean-Paul van Mendegem, who was my first PhD student in philosophy, and in logic, because before I had someone in ethics in Brussels. But Jean-Paul is a mathematician who was teaching in Brussels all the time, and I wrote him something with the following idea. Suppose that an inconsistency is found in piano arithmetic. Then you can show by applying some adaptive things, you can still say, well, let's now interpret this as consistently as possible. And then you can show, said roughly, that nothing changes. So, which is basically
Inconsistencies are not a problem if you ignore them.
Yeah. No, but if you, it's not a matter of ignoring them. Because if you apply standard adaptive methods to it, remember that you have, semantically speaking, you have for piano arithmetic, you have models that are countable, and then you have models, that also may be countable, I'm sorry, but you have models that you have non-standard models. You have the standard model and you have non-standard models. And if an inconsistency arrives, you may simply add to piano arithmetic something like there is an x such that, and then an inconsistency, for example, x is different from itself or is its own successor or whatever. And then you can, by reshuffling a little bit the piano axioms, sometimes using contraposition on them, and so you can phrase your adaptive logic in a rather controllable way. And what happens will be that this exceptional x, that is, for example, identical to its own successor, will be in a non-standard block. But that means all you can show is there is an x such that x is identical to the successor of x. But of course you can, since in your non-standard blocks, the elements of that have no names, at least not the standard names that you arrive by a zero and a number of consequence, number of primes. So you get not a new inconsistency. Like if 7 would be its own, then if you would have 7 is identical to the successor of 7, and that would be a new inconsistency in the theorem. But if you claim just there is one, well, that doesn't add a new inconsistency to what you have. So reasoning from that point of view, whatever you could say about the numbers of the standard model would basically remain the same. We know the problem of not being able to characterize the standard numbers of. That's something else. But nothing would basically change. So in that sense, definitely your idea was correct. You can find most of these papers. They are nearly always on my homepage. My homepage was on the first page of the slide. Because I just, yes, please.
This might be an example. Even in count of set theory, once you freeze the set of set, you use the rest, it's working. Mathematics together.
I have a paper study Lógica on that, appeared in 22. And what do I want to say about it right now? Well, the funny thing is that you have, suppose that ZF is consistent, which most mathematicians believe. CF or ZF, C doesn't matter. Suppose it is consistent, then you can produce an adaptive Frege set theory that makes true all roots of ZF. So it makes all ZF sets consistent. So whenever something is a member of the set, it's not a non-member of the set. Okay, an inconsistent set is one of which a non-member is also a member. Okay? So you can show that in that kind of construction, you have all the ZF sets, and moreover, you have a lot of consistent sets, different consistent sets, that you cannot express in ZF. Like, for example, you can take the members of the Russell set, and they will form, in that construction, a consistent set. not the Russell set itself, of course, but the members of the Russell set, and also the non-members of the Russell set. You can define as a consistency.
By extensionality, wouldn't that be the
Sorry?
by extensionality?
Extensionality is tricky in those,
Okay.
in that region. But why would it?
Members of the Russell set is the Russell set.
The set of members of the Russell set is the Russell set.
You think so?
Oh, that's what he said.
You always have to define it in terms of your logic, of course. Because what the way Joanne now translated what you said was in a kind of intuitive way. Okay? But suppose you say, well, the set of all x such that if x is a member, the set of all x's for which it holds that x is a member of the Russell set.
Okay.
It's not obvious that in a paraconsistent context you can derive from that it is essentially identical to the Russell set. Because given the fact that you have inconsistent sets, you have, in order to show extensionality means if two sets have the same members and the same non-members, then they are identical. That's one of the defenses that Zach Weber is a student of Zach Graham Priest, and well, everybody can write Weber, I suppose. He's now teaching in New Zealand, took his PhD in was not in Brisbane, in Melbourne.
At the moment.
Maybe it's even at the moment in Bochum, yeah. Graham has good relations with Diderik. So Zach tried to formulate with the help of a relevant implication, a Frege set theory. It's very different from the adaptive one in the sense that his set theory is based on a Tarski logic. Okay? So in that sense, it's very different. And people kind of argued that look, you can have sets that have the same members and are nevertheless different. And so he wrote a paper in I have to check it. I would have to check. I'm sorry, but I can't find it. I can't find the reference in my paper. He wrote a paper saying that, yeah, well, for example, there's the empty set with all sets in the. It was not a good example. I'm sorry. You can have a universal set of which the complement is which E has complement defined by the paraconsistent negation, and the complement is completely empty, and you can also have an empty set that, a universal set that has some sets in its complement. You can even have a universal set that has all sets in its complement. That's a very interesting set, which also plays in my construction plays a very important role. Like there is an X such that X is a member of itself and X is not a member of itself. Of course, this is a theorem of inconsistent set theories because Frege set theories, because the Russell set is a set in Frege set theory. So there is a set that is a member of itself as well as not a member of itself. But now, what is in the complement of the set that you characterize like this. So D, Y such that. So here you write a closed formula. That is very typical that to understand the trick. You write the Y or whatever here for which this holds. And this is a theorem of Frege's set theory. Now, what is in the complement of it? The negation of this is a theorem of logic in the thing. Namely, it is for all x, either x is a member of itself or it is not a member of itself. Which is very reasonably a theorem of logic and Zach's underlying relevant logic. Okay? It's either something is a member of itself or it is not. You want to have that. Even classical logicians want to have that. So that means that the complement also contains all sets. All sets. Okay? Because the complement of this set are the things that fulfill the negation of this formula. But every y fulfills the negation of that formula.
Are they equal?
Sorry?
Are they equal? This set and the complement?
Well, they're equal. Well, yes, in this sense that they have the same members as well as the same non-members, namely everything. Yeah. I was first a bit confused, but yeah, they are equal. And it's not nothing disastrous follows from it. But of course, you can say this is clearly not the universal set, because the universal set has an empty complement. The non-members are, the set of non-members is empty. Whereas here, the set of non-members contains everything. So I think the point Zach makes in that paper is absolute. I think it was published in Studia Lógica. I think it is absolutely correct. There's nothing wrong with his reasoning. There are other problems, but there's nothing wrong with it. So the other problems is that his set theory, just like all the set theories that Grand Priest ever created, do not fulfill extensionality fully. Because there are sets that have the same members as well as the same non-members, and that nevertheless are not provably in the theory provably identical. And that is because Zach's set theory is based on a relevant implication. For Graham, the reason is different. And so a relevant implication to prove set identity, you need relevant equivalence. And there are many things that are extensionally equivalent but not relevant. So it's extensionality is defined really as in terms of an intentional operator, which is funny. Okay? It's not what Frege would have considered extensional. Frege simply meant have the same members. Okay. Well, I'm glad there were many questions. That's okay again. My daughter-in-law tried to convince me that the painting, she did not like the painting because the breasts were not natural, she claimed. And then she used a very bad argument, namely that she should have now not to use against the philosopher. Namely, she said, my breasts are completely different. So I told her there are breasts in all measures and weights. That's an expression in Dutch. I should have added forms, of course. Yeah, now I lost it again. Laughing at. What's so funny?
We saw your password. We just saw your password.
You press the button that shows the password, right?
Yeah, so what? Eduardo, I gave my PIN code to Eduardo because I could not use it, my PIN code for the phone, because I couldn't open the phone.
Now, right forgot the word.
Yeah, I was sure you would have forgotten. Is there anybody that still remembers my password for?
It's recorded.
It's in the. Yeah.
Great.
So now you can see an adaptive logic as acting on premises between the lower limit logic and an upper limit logic. The lower limit logic, what follows by the lower limit logic follows always. So that's the kind of stable part of the consequence. That's the tasky part of the consequence. Lower limit logic is the tasky logic. Okay? The deductive part, you could say. And then the upper limit logic is a kind of maximal if there are no abnormalities among the derivable from the premises by the lower limit logic, then you get the upper limit logic. And to apply to paraconsistent logic, for nearly all paraconsistent logics, the upper limit is classical logic. The lower limit will be the paraconsistent logic itself, of course, and then the adaptive consequence set will vary in between. And you can show, I will give some meta theory at the end of the series. You can show that there is a definite set of abnormalities that you consider as false and a specific set that you consider as true, namely those derivable by the lower limit logic, and so on and so on. What else did I want to say? Yeah, so the person, I announced that yesterday, the person that applies the adaptive logic does not have to do anything, in the sense that the logic determines what are the adaptive consequences on top of the lower limit consequences. It's basically a definition of a consequence. So this is a purely conventionally defined things, and you will see why. We use in Ghent corrective adaptive logics, the term corrective, for the case where a certain standard logic, which we take to be classical logic, a certain standard logic leads to triviality. And then you say, well, now we have to, our adaptive logic has to correct this by not concluding to triviality, rather avoiding triviality, but nevertheless, by considering the premises as consistent as possible, and hence going as far as possible in the direction of the upper limit logic. Sometimes, like suppose you take a logic of inductive generalization. Everybody knows that the generalizations you hope to derive from a set of data are not classical consequences of the data. Okay? Because then you cannot derive general claims from specific data, from particular data. But sometimes it depends on your interpretation. Like Grand Priest claims that the true logic is the logic he calls LP, the logic of paradox, which was actually not discovered by Graham, but rediscovered by Graham. Asenko, who was a professor of math in Pittsburgh in those days, had written a paper on, I think he uses not antinomy, but he uses one of those Greek words like antinomy, but it is not antinomy. It's another term.
It wasn't in Pittsburgh, it was in
Sorry?
Buenos Aires when he did it.
Yeah,
Yeah.
did he do it already in Buenos Aires?
Yeah.
And then he has redone the thing together with a student of his, and there his thing is literally grams the same as LP, what Graham later called LP, but the redone the new version has a classical implication in it, and for that reason has a number of, in a sense, nicer and less wild properties. Like, for example, in LP, every set of formulas has a model. That's not the case in the system Asenko created together with his student. Because with material implication, you can easily cause triviality by, you can have finite sets that lead to triviality, according to that second logic. But I mention it because Asenko is often forgotten in the context. Everybody talks about Graham Priest, and of course, Graham made it popular LP, but he was not the first creator of the logic, or the first, or the, what do you say, discoverer of the logic, or is a logic devised or discovered?
Let's not get into
Okay. So for Graham, as LP is the correct logic, he will consider that as the criterion, where I consider classical logic as a criterion. Considering classical logic as a criterion is simply for distinguishing between corrective and ampliative. So referring to classical logic is because classical logic is so extremely popular also in the sciences, not only with mathematicians, also with physicists. But if LP is true, then of course the paraconsistent logic is at the same, a logic that corresponds to my adaptive logics will by Graham be considered as ampliative because it gives you consequences that transcend your LP consequences, but are still below classical logic. Okay? But for him, that's the point where you go well. For the rest, it does not have the slightest importance because these ampliative and corrective logics have exactly the same formal property. So you don't have to care about, doesn't make a difference. So, was there somebody that yesterday somebody wanted to give me a warning, which I never received or never saw it, but I'm afraid that the same thing is happening
About
today.
10 minutes, 15 minutes.
I still have 15 minutes, okay. But I want to leave some time for more questions.
So,
Because it's better not to enter. This is really a new topic.
so this 15 minutes is already for the question. Will be already for the question.
Okay. Any more questions? And then I leave that for tomorrow. That's the development of the dynamic proof theory. Now we had many questions while I was talking. So if there are no, please, yes.
I'm very sympathetic to this idea that all reason is defeasible. And And I'm also sympathetic to the thesis that all theories, at least in principle, are defeasible. Maybe not as of right now, but maybe at a later time. So I'm basically accepting most things you're defending, but I think there might be a problem here when you're trying to decide between conflicting reasonings or theories. Because if you don't think they're all reasonings and theories are feasible, you can say, well, I have a criterion to decide between two theories. If theory 1 is defeasible, I'm going to get rid of that. If theory 2 is not, I'm going to go for theory 2. So my question is, how can you decide between those two theories, given the fact that they share a common property, namely the property of being defeasible? Because I don't think you want to go full relativistic. You want to have some kind of hierarchy between distinct reasonings and distinct theories, but it's not clear to me how can you have that. I mean, what would be the ultimate criteria then to decide between two conflicting theories?
Well, but the theories can have a completely different content, can be phrased in different languages. We often think about language schemes when we think about logic. But of course, when you apply the logics, you apply them to specific theories. The language of that chemistry is written in is not the same as the one that psychology is written in.
Yeah, but on a follow-up of this question, what if he meant on the same domain, two theories of the same domain?
Yeah,
right?
Yeah. Are you saying that there is no conflict? This is more or less the
But there still will be a difference between, at a certain point in time, the two theories will have certain theorems. And the theories are identical if their non-logical theorems are, the sets of non-logical theorems are identical. If that they are both defeasible does not say anything about identity. So the least you should require of an empirical theory, for the identity of an empirical theory is, two empirical theories are identical if they define the same set of non-logical consequences or non-logical theorems.
Yeah, but I'm assuming the theories are different, not they are the same theories. It's why there is a conflict between them. They don't agree in all theories. There's a conflict, and I'm trying to figure out, would I go for theory 1 or theory 2? I know that they're both defeasible, and I need a new criterion to figure out which one I'm going to decide. And they're not the same theories.
That's, I wonder to what extent this is not a theoretical question in the sense that to claim it in general for defeasible theories, I think is hard to prove much about it. But for adaptive logics, there is a paper written by Peter Verday, maybe in another order, I'm not sure. Peter Verday, Christian Strasser. He's in Bochum, Verday is in Louvain-la-Neuve, and then me. And this is, again, would have to look for the reference. It also was published in Lógica Analyse. It's only like, I think, 10, 12 years old. And we showed that you have a very nice identity for theories defined in terms of adaptive logic. So a theory defined in terms of an adaptive logic has a set of non-logical axioms and then an adaptive logic. And we showed that you have nice definitions to define identity in that case. So this is more than a vague claim because there is a proof over there. Yeah. But I must admit that I don't remember everything of it. But, I suppose it will again be open on the internet somewhere. At least the so-called preprint, which does not contain the latest changes, otherwise you get in trouble with Glue. Which is not too bad.
Last question, please.
I have a doubt about the consequence operator. You were saying about the consequence operator, about the loss of monotonicity. If you have, regular rules of inference,
What are regular rules of inference?
you know your rules of inference, like what's on and secret calculi, something like that. If you have rules of inference, you know what to take from what. You have the set of formulas in some language, and you know you have your set of formulas.
Yeah, but if you pick rules of inference of a specific form, all these have been worked out, but I don't have it all in my slides. So if you say you have a rule of inference is something of this form, where you have, say, delta, which is a set of formulas, and then here a formula. Here's derivable from delta. If you have all formulas of this form, then you can derive A from it. If you do it like that, you always have a Tarski logic. So I'm a bit afraid that when you say if you have regular rules, that you actually mean Tarski rules. And of course, yeah, if you have Tarski rules, you will have a Tarski logic. Because otherwise you need typically adaptive rules that, well, they are here, but you will see them tomorrow. No, these things are different, as you see. For example, you have stuff like if B or classical disjunction, a classical disjunction of abnormalities, the theta are abnormalities, and then if this is derivable from a set of premises, then, and if you have the premises, local premises, if you have them in your proof, each on a certain condition, then you can derive B on the union of these conditions, and I'm sorry. And actually, I've also paper about that. No, that will not work. So these rules are clearly not Tarski rules because they also refer to conditions. And in Tarski rules, you just have from those formulas, if those formulas occur in your proof, then you can derive another formula in the proof by an application of this rule. Whereas this also refers to conditions. So here the lines in a proof are not only like in Tarski logic kind of number here. So some number of the line and then a formula, that is the formula derived of the line, and then a justification, which is usually a set of formulas, something referring to a set of lines that occur before, a set of formulas that occurred before in the proof, or to the lines of those formulas, and then a rule. But in adaptive physics, you have moreover this condition here, which is always a set of abnormalities. And then the rules will be more complicated as a result of that.
The consequence operator, like it will take the abnormalities as arguments.
Which operator?
You can think that the consequence operator needs to take the abnormalities as arguments as well. The more complex consequence.
You can, Christian Strasser has amused himself with that, or rather a doctoral student of his, amused himself if you add classical operators in your language. You extend your particle system language with classical operators, basically classical negation, for example. And then you can push whatever is said about conditions in the standard format, you can push all that to the premises. Because remember that the idea was this line, the idea is A is derivable from the formulas of those lines by a certain rule on the condition that all formulas in this set are false. Now, of course, if you have classical negation in your extended language, if there is here an, let's say, abnormality A1 to abnormality, no, should not be A, should be B, B1 to Bn, for example, you can, of course, require to have in your premises not, this is a classical negation, not A1 abnormal up to not B1, not Bm abnormal. But this is simply a kind of rather simplistic transformation to comes exactly to the same thing.